functional groups. We talk about functional groups. We talk about alcohols, aldehydes, ketones, ethers. What else we talked about? Alkenes, alkynes, all kinds of functional groups. Now we're going to talk about carboxylic acids, and there's different types of carboxylic acids. There's aromatic carboxylic acids, and aromatic means it has a benzene ring. Those are your aromatic carboxylic acids. And you've got aliphatic carboxylic acids. Aliphatic means everything besides a benzene ring, all your other hydrocarbon chains. Okay, so you got aromatic carboxylic acids and aliphatic carboxylic acids. Okay. So your aliphatic and aromatic esters also. Okay, we talk about ethers. These are esters. Okay, esters are a carboxylic acid. Instead of the H here, we have an R group. Then it becomes an ester. So this just happens to be on carboxylic acids and esters. Again, carboxylic acids have an OH at the end. Esters have an OR at the end, or aromatic. Okay, you can have an aromatic on both sides or on one side. So those are aromatic esters, and they have aliphatic esters also. So it's just like the difference between aldehydes and ketones. Aldehydes have a hydrogen, ketones have a carbon group at the end of it. Okay, after the carbonyl group. With carboxylic acid, there's a hydrogen at the end of carboxylic acid. With esters, there's another R group after it. The same between aldehydes and ketones. Same relationship. So an ester, okay, this is the carboxylic acid. Okay, this is, well, we'll learn how to name in just a second, but this is a propanoic acid, propanoic acid, 3 carbons. Okay. It has an acid because it is COOH group on it. Okay. The esters have an R group in place of this hydrogen right here. So the hydrogen has been replaced with an R group. Then it becomes an ester. Okay. And this is methyl, because you named the group that was part of the alkyl before, and it was going to do a little bit, and then ethanoate. That's how we name esters. Okay, we'll get into that as we go through the chapter. We'll learn how to name these things in this chapter. All right. So this is where we're headed. Let's see if this will go on. It didn't change. There we go. Sleeping genes, as we use old Beetle titles. So a common carboxylic acid, butyric acid. Butyric acid is a carboxylic acid, butane, which has 4 carbons. Holds a promise of being an effective treatment for 2 age-old genetic diseases. Okay, so butyric acid is 4 carbons and a carboxylic acid, COOH, and everything else is hydrogens. CH3, CH2, CH2. Okay, that's butyric acid. Okay, sickle cell anemia and beta thalassemia are 2 very dangerous and deadly genetic diseases. Some of the new treatments for it involve butyric acid. Okay, so both human genetic diseases of the beta globin portion of hemoglobin. Remember, hemoglobin consists of 4 chains, 2 alpha chains, 2 beta chains. Okay, the beta globulin portion of hemoglobin, the protein that carries oxygen from the lungs to the tissues throughout the body. Okay, so hemoglobin, remember, 2 alpha chains, 2 beta chains. The beta chains is what binds the oxygen and carries that to the different tissues of the body. Okay. Normal hemoglobin, we just said, consists of 2 alpha globin proteins and 2 beta globin proteins. Okay, and there's 4 heme groups with that. The heme group is the iron bonded to the porphyrin ring, and that's what actually holds the oxygen in place on the red blood cell. Okay, so there's 4 of those groups in every hemoglobin molecule. Okay. In sickle cell anemia, okay, there's a faulty B globin gene, calls for the synthesis of a sticky form of hemoglobin that forms long polymers. Remember, polymers are groups that stick together. Okay, so now these red blood cells stick together and they clog in the blood system. If they're clogging the blood system, they're not absorbing oxygen. They're not allowing it to transfer oxygen throughout the body. This distorts the red blood cell into an elongated sickle shape. So instead of your red blood cell being a bifurcated round disc, it now takes on this shape as it sticks together of a sickle. And that's where the disease gets its name, sickle cell anemia. Okay. Once it's in the sickle shape, it gets stuck in the capillaries because they tend to stick together and coagulate. So it blocks up your capillaries and it cannot provide oxygen needed by the tissue because it blocks the arteries that are delivering oxygen, and it's defective in its form, so it's not holding or absorbing oxygen from the lungs. So you got those two factors going on in sickle cell anemia. In beta thalassemia, there may be no beta globin produced at all to hold oxygen. Okay. This results in short-lived red blood cells and severe anemia. Both result in severe anemia. Now, red blood cell normally lives, who took my anatomy class? Who remembers? How long does red blood cell live? Red blood cells live about 120 days, then they're replaced. Okay. So with beta thalassemia, they don't live that long. They actually cut in half. They live only 60 days. Okay. Both these diseases do not affect the fetus, though. Okay. So think about it. So if the mother has sickle cell anemia, it's not going to affect the fetus because before birth and for several weeks after birth, fetal globin is made rather than adult beta globin. So the gene that codes for the beta globin gene is not even being used yet in the fetus. It only occurs after the fetus is born, and then they stop making this fetal globin or fetal hemoglobin. So an infant, the fetus produces what's called fetal globin rather than the beta globin gene. So the defect isn't shown yet in the fetus. Okay. The fetal hemoglobin is made up of 2 alpha chains that are replaced by the 2 beta globin chains as the infant ages. 2 gamma chains, I'm sorry. So the fetal globin has 2 gamma globin chains instead of the beta globin chains. So it still has 2 alpha, but the fetal one has 2 gamma globin chains. Okay. Fetal hemoglobin has a stronger affinity for oxygen than the adult form. So when it's at the placenta, what's going to happen? The fetal hemoglobin is going to suck the oxygen off of the mother's red blood cells. Okay, that's what it does. The fetus gets enough oxygen even at the expense of the mother. Okay? Because fetal hemoglobin has a stronger affinity for oxygen than the mother's own hemoglobin. Okay, so it's going to get, the baby's going to grow. Okay, it's going to get the oxygen that it needs. Okay, it has a stronger affinity for it. There's 2 observations led to the possible treatments for both these diseases. Physicians have found that some sickle cell anemia patients who suffer only mild symptoms, okay, they continue to make high levels of fetal hemoglobin. In other words, their body doesn't shut off the gene that makes fetal hemoglobin, because knowing when the baby's born, the gene shuts off her fetal hemoglobin and starts making the beta chain for the hemoglobin, and it gets to the normal affinity for it. So now if the baby has, once the baby's born, if it has sickle cell anemia and it doesn't shut off that fetal gene, it's going to still make fetal hemoglobin have a higher affinity for oxygen and be able to function normally. Okay. And second, that as some babies born to diabetic mothers continue to produce fetal hemoglobin for unusually long times afterwards. Okay. Those 2 factors tend to affect the production of fetal hemoglobin after the baby's been born. Okay. Coincidentally, there's an unexpected high concentration of amino butyric acid. Okay, an amino group we haven't gone into yet, but amino group is just NH2, ammonia. That's an amino group attached to a butyric acid. Okay, butyric acid is our 4-carbon carboxylic acid. Okay, it's a modified carboxylic acid in the blood of these infants. So high levels of this ammonium butyric acid, okay, is found in the infant's blood. Okay, and this is what it looks like. Just like that. It's an NH2 group. This is ammonia. So this is ammonia. And then we have 1, 2, 3, 4 carbons, butyric acid. Okay. This is what apparently triggers the gene in these babies born that keep making this fetal hemoglobin that allows them to function normally with the sickle cell trait. Okay, the sickle cell blood cells still produce, but these allow it to keep going because it replaces. You're not coding for that beta chain anymore. You're coding for the fetal chain, which is gamma chain, and that allows you to absorb oxygen at a higher rate, which is really kind of interesting. So Susan Perrin at the Children's Hospital, Oakland Research Center, decided to try reawaken the dormant fetal gene globin. Remember what happens when the baby's born? It shuts off the fetal globin gene, and then starts producing the beta gene. Remember, it's 2 alpha and 2 beta. Okay, so once that fetal gene is shut down, then the sickle cell trait comes out, the red blood cells are formed, and the baby has severe anemia. Now, if the fetal gene gets turned back on, you're going to make more of that gamma chain, that fetal chain, and allow a higher affinity for oxygen, so the baby's not going to have anemia as it grows. Okay, so Sheena College injected a sodium bitrate solution, which is the sodium salt of butyric acid, which we talked about, the 4-carbon carboxylic acid, into 3 sickle cell patients and 3 beta thalassemia patients. Okay, so you're given higher levels of a butyrate solution. Okay, this butyric acid. As a result, okay, of the 2 to 3 treatment, fetal hemoglobin production was boosted about 45% in these individuals, which is going to be a great, shows a promise for great treatment for sickle cell anemia and for beta thalassemia. Okay, one beta thalassemia patient even experienced a complete reversal of the symptoms. Now, beta thalassemia can be fatal, okay, because you're not producing that beta chain of the hemoglobin. You're not getting oxygen to your tissues. And then we can inject them with a butyric acid compound that's going to stimulate that gene to produce more of that sickle cell, that produce more of that fetal hemoglobin. They can live normal lives. It's amazing what you can do with it. We'll get into the DNA and turning on the gene stuff too, coming with our biochemistry part of this. But it's a really promising treatment for both beta thalassemia and for sickle cell anemia. And it's a very simple treatment. Okay, longer studies with larger numbers of patients are going to be needed. This only study with 4 patients, so but it shows promise. It shows that all have a 45% increase. Now, how long it's going to last, how we keep that gene turned on, there's a whole lot of things that need to discover, but that is an unbelievable start. It's a great marker in research. So we might have a cure for that. Pregnancy results hold the promise of a full and active life for individuals who were previously limited in activity and expected a short lifespan. Okay, both sickle cell anemia and beta thalassemia really shorten their lifespan and very limited activity because of severe anemia. They couldn't function in normal life. And now these people can live normal lives with a regular lifespan if this treatment succeeds, is what it's going to, which is unbelievable. All right, carboxylic acids. That's our starting a chapter with. You have the old familiar carbonyl group right here. There's our carbonyl group, and now we got a hydroxyl group attached to it. Like I said, it's just like our aldehydes and ketones. Okay, same kind of relationship. The carboxyl group with hydroxyl group attached to it. Okay, the structure of it: carboxylic acid group consists of 2 polar functional groups. Okay, remember the carbonyl group. Oxygen's more electronegative than carbon, so it's delta plus and delta minus. OH, delta minus, and the H is delta plus. So now you got 2 polar functional groups. Remember, so alcohols have hydrogen bonding. Carboxylic acid have hydrogen bonding with this hydrogen right here. It's attached to the oxygen directly. So you have hydrogen bonding and you have a second polar group. So carboxylic acids are going to be more soluble in a polar compound like water than even alcohols are, because they have 2 groups that are going to function as polar groups and with hydrogen bonding. So they're going to have higher melting and boiling points, going to be held together tighter. Okay, and they're going to be more soluble in water or other polar compounds. Okay, because you have the carbonyl group, C double bond O, and you have the hydroxyl group, OH. Both those groups are polar. Like I said, oxygen is more electronegative than carbon. Oxygen is more electronegative than hydrogen. And with hydrogen, with a hydroxyl group, you also have hydrogen bonding to another OH group. So physical properties are going to deal with those two polar groups now. So if we have low molecular weight carboxylic acids, okay, they're going to be very sharp and very sour tasting. Okay, they're unpleasant aromas. They do not smell good. Right? High molecular weight carboxylic acids. Okay, these are fatty acids, which are really important in biochemistry, which are going to go into in great detail. I think it's in chapter 18 or 19. We'll get into the biochemistry of fatty acids. Okay, so low molecular weight carboxylic acids are water soluble. Okay, due to hydrogen bonding with water. Okay, and with each other. Okay, so once you have that hydrogen bonding, you have the other polarity, it's very soluble in water until they get where the long carbon chain overpowers the functional groups. Then it becomes insoluble. Okay, so here's your hydrogen bonding. This is your carboxylic acid. Here's your R group. Here's your carbon. That's your carbonyl group. And there's your OH group right there. So this will have hydrogen bonding. You see the red dots that connect it to another carboxylic acid, and hydrogen bonding to the water molecule. So it's bonding both to the water molecule and another carboxylic acid molecule with hydrogen bonding. And you also get this carbonyl group with a negative charge also, which will bond to the positive ones of water and the other end of the other carboxylic acids. Okay, so the important point is you're getting two functions here. You're getting the polarity and you're getting hydrogen bonding, which makes them very soluble for low molecular weight carboxylic acids in polar compounds. Okay, so due to the carbonic acid forming an intermolecular hydrogen bond, okay, boiling points are higher temperatures than would normally be expected. Boiling points are going to be higher temperature than those of other functional group studied. So far, we've had ethene, we have alkenes, alkynes, we have had alcohols, we've had aldehydes, we have carboxylic acids, we've had ethers. Okay? So the carboxylic acids are going to be the highest boiling points that we've had yet because they're the most polar. They have two functional polar groups at the end of it. Okay, so if we look at ethanoic acid, this is a carboxylic acid, low molecular weight. And if we look down this chart here, we see that the molecular weights are about the same size. Okay, so they're roughly all the same molecular weight, same size. If you look at the boiling point of the carboxylic acid, it's higher than any of the other compounds. It takes more to break those molecules apart that are being held together because it has two polar groups and it has hydrogen bonding. The alcohol of similar molecular weight has hydrogen bonding and one polar group. Below that, you have the ketone, which is a carbonyl group. And you have the aldehyde, which is a carbonyl group. Just the polarity of the carbonyl bond. And these are real close in boiling points, melting points. Okay. Then you have the ethers. Ethers have very little polarity, but they have some of that oxygen there. So it drops down a whole bunch from there. And then this is your hydrocarbon, which has no polarity. It's like -5 poles apart. Okay. So your molecular weight, as long as it stayed the same, the boiling point increases with the amount of force that's holding that molecule together to another one of its kind. All right. And with the carboxylic acid, that's our most polar group that we have so far, as far as boiling point goes. Okay. So as with alcohols, the smaller carboxylic acids are soluble in water. Okay. Solubility falls off dramatically as the carbon content of the carboxylic acid increases. As you get a longer hydrocarbon chain, then it starts to outweigh the effects of the polar groups of the end because the carbon chain is nonpolar. And as long as it's small enough, it's not going to affect it. But that chain gets longer and longer and longer, then it's going to overpower the effects of the COOH group, the polar end of that molecule. Okay? It becomes more and more less polar as you increase the hydrocarbon chain, the size of the chain. Acetic acid. Acetic acid is ethanoic acid, 2 carbons. Okay, that's vinegar. That's what gives vinegar its smell. It's completely soluble in water. Okay. So acetic acid, completely soluble. Hexadecanoic acid. hexadecanoic. Decane is 10, hexa is 6. So this is 16 carbons. Okay, 16 carbons, okay, it's found in palm oil, is insoluble in water because your hydrocarbon chain just got so large that it overpowered the polar group of the carbonyl group and the hydroxy group. Okay, so the lower molecular weight carboxylic acid has a very sharp, sour taste and a very unpleasant aromas. They do not smell good. Okay, formic acid, okay, which is methanoic acid, 1 carbon, okay, is used as a chemical defense by ants. That's what causes the burning sensation of an ant bite. You ever get bit by these red ants in 29 Palms out in the desert here? They burn. They're not like regular ants you find down the hill, okay? The desert ants, when they bite, they really burn. And it's burned because they release formic acid, which is methanoic acid, which, if you want to draw it out, it's just 1 carbon. Okay, and that's methanoic acid. That's the formic acid. That burns through your skin. Okay, that's what causes that burning sensation when those ants bite out here. Acetic acid. This is vinegar. It's found in vinegar. Okay, this is ethanoic acid. It's 2 carbons. Propanoic acid is 3 carbons. And that's that tasty, that real tangy thing you ate with Swiss cheese. Okay, that flavor, that smell you get sometimes with Swiss cheese. Butyric acid, which we just talked about, that we inject into certain people that are actually turning this gene on for the phenylhemoglobin to release gamma chains and not the beta chain, so the people can live long, healthy lives. Okay, this causes the smell you get when butter turns bad. Okay, and gangrene. I don't know if you ever had a patient that's had gangrene on a digit, foot, or hand. It is not a good smell. It can make you sick smelling that stuff. Okay, that's when you put you have patients like that. A trick to do is when you wear a mask, you spray like the stuff you gargle with, chloroseptic. You spray that in your mask because it's a really strong smell, and you put your mask on. That way, it masks the smell of the gangrene. It's a really good trick for when you have patients like that. It's a really good trick in autopsies too, especially if they've been underwater for a while and they get that bloated, that methane gas. That does not smell good. So you just spray your mask with that stuff, and it helps a lot. For those of you low molecular weight carboxylic acids, they do not smell nice. Okay. So assuming that each of the following pairs of molecules has the same carbon chain length, okay, so each one's going to have roughly the same size, which members of each of the following pairs has the lower boiling point? Lower boiling point. Remember, if something's being held together, if this molecule and this molecule is being held together, okay, the lower molecular weight means they're not being attracted. That means you heat it up and they blow, the intermolecular forces come apart. So you're not getting a very strong bond. So which one has the lower boiling point? Okay. And the circle came in first. That's not good. Boy, all the circles are coming up first. Carboxylic acid or a ketone? Remember, carboxylic acid is RCOH, and the ketone is RC1R. Okay. This one has 2 polar groups and hydrogen bonding. This one only has 1 polar group and no hydrogen bonding. So the lower boiling point is going to be the ketone, okay? Because it has less forces holding the molecules together, so it's easier for those to break apart and boil at a lower temperature, okay? So no matter how I ask the question, you'll be able to answer, right? I could say higher boiling point or lower boiling point. If it's a higher boiling point, you have greater forces holding it together. If it's a lower boiling point, you have less forces holding it together. I got to fix these slides that show the circle first. Takes away the challenge. A ketone or an alcohol? Ketone was that. Alcohol was, okay. Look at each molecule. The ketone has 1 polar group. The alcohol has 1 polar group, but the alcohol also has what that's going to attract it together?
Hydrogen bonding.
Hydrogen bonding, perfect. Okay, so you got hydrogen bonding plus a polar group. So that's going to hold together tighter. So the one with the lower boiling point is going to be the ketone. Okay. This one didn't have the group. This one doesn't give you the answer. You have to think about this one. Okay. An alcohol or an alkane. Alcohol is an R, OH. Alkane is just an R group. So he's got the carbon chain. Okay. So the alcohol has one polar group and hydrogen bonding. The alkane has no polar groups and no hydrogen bonding, obviously, if there's no polar groups. Okay, so which one's gonna have the lower boiling point?
Alkane.
Alkane, perfect, because there's not as much holding it together. You got it. So we can tell a lot of physical properties and predict a lot of behaviors by the function groups that are attached to the hydrocarbon chain. Okay. Assuming it's compared to the same thing, which one has the lower, again, lower boiling point? Make sure when you're taking my exam, you look at whether and circle or do something where it says lower or higher boiling point so you know what you're looking at. Okay. Make sure you understand if it's lower or higher. I did the arrows again. I have to fix those. An ether or an aldehyde. An ether is R, O, R. An aldehyde is R, C, O, O, H. Okay, they're going to be kind of close, but there's one polar group here, and it's not quite as polar here because there's oxygen's being shared between. This one, the oxygen only has one R group attached to it. So this one's going to have a stronger attachment because it's not being shared. It's not pulling those electrons and distributing them across. The electrons are all concentrated right there. So this one's going to be more polar. It's a more polar functional group. So if it's more polar, it's going to have a higher affinity to bind to molecules of its own kind. Okay, so the one with the lower boiling point is going to be the ether. Okay, an aldehyde or carboxylic acid. That's going to be easy because we know carboxylic acid is the highest that we got so far. Aldehydes are, carboxylic acids are one polar group, two polar groups plus hydrogen bonding. So which one is going to have the lower boiling point? And it's already circled for you. So the aldehyde, right? Okay, because it only has one polar group versus the two. Carboxylic acid so far is the highest boiling points and melting points of anything we talked about so far, any of the function groups yet. All right. And this one you got to figure out now. It didn't have the circle come up beforehand. I'll have to fix those. An ether, which is R, O, R, or an alcohol, which is R, O, H. Again, one polar group, but not very strong because it's being pulled by two R groups. So this has a strong polar group plus hydrogen bonding. So this one has more forces holding those molecules together, higher boiling point. So which one have a lower boiling point?
Ether.
The ether, perfect. It didn't line up very good either on that one. Okay, would you predict that a carboxylic acid would be more polar or have a higher boiling point than an aldehyde of the comparable weight? So would the carboxylic acid be more polar, have a higher boiling point than an aldehyde? Carboxylic acid, yes, perfect. And aldehyde. Okay, again, carboxylic acid has two polar groups and hydrogen bonding. It's going to have a much higher boiling point. It's going to be more polar than an aldehyde of the similar molecular weight. So the carboxylic acid has two polar bonds, carbonyl group and the OH, and it has hydrogen bonding.
Kitchens.
Okay.
What do they call you?
Okay.
Lebanon?
Okay. Sounds good.
Want to take a pain pill?
Okay. All right. So the aldehyde only has one, the carbonyl group, as being polar. So you would predict that. Okay. Would you predict carboxylic acid to be more polar and higher boiling point than an alcohol of comparable molecular weight? Okay. Carboxylic acid, alcohol. Okay. Again, polar group, hydrogen bonding, and an extra polar group. That extra polar group gives you more polarity, has a higher boiling point than the comparable molecular weight alcohol. So same thing. You still answer yes, right? Everybody would answer yes. Okay.
Yes.
Okay. So the carboxylic acid would have the higher, whoops, why did it click off again? Okay. Alcohols only have one polar group, the hydroxyl group. All right. So those are our physical properties of carboxylic acids. Any questions with that? Sometimes I start talking, I just get on a roll and forget to slow down and ask if anyone has any questions. All right, perfect. So how do we name carboxylic acids? Just we've been naming everything else. So this is a carboxylic acid because you can tell because there's a COOH functional group. That's a carboxylic acid. Okay, we always number from the carbon of the carbonyl group. So this is always number one. There's no looking at the chain to see of which functional group is before, because carboxylic acids are always at the end of a compound. Why? They end with hydrogen. If they end with hydrogen, remember all our Lewis structures? Hydrogens are terminal. You can't put anything past this hydrogen. You can't put another bond here because hydrogen only have one bond. So carboxylic acids are always terminals. They're always going to be the number one position. There's no decision here. So it's always 1, then 2, then 3, then 4. Okay, so we have 4 carbons. 4 carbons is butane. Right up in the corner, so won't get in our way so much. 4 carbons is butane. When we name a carboxylic acid, we drop the E. Okay. So now I have butane, and we add OIC acid. Okay, so instead of a butane, now we have butanoic acid. So we drop the E, add OIC. Okay, and then we name our substituent groups. We have a bromine group at number 3. So this would be 3-bromo-butanoic acid. Okay, so determine the parent carbon chain, which we said was 4 carbons, and that's butane. Okay, we number the chain, so the carboxyl carbon is carbon 1. Always. Okay, so there's 1, 2, 3, and 4, just like we numbered. Replace the E, so drop the E and add OIC acid, oic acid. This is what we did. And then so we have butanoic acid, and then we add our substituent. If 2 carboxyl groups are present, we use dioic acid. Can you ever have 3 trioic acid? Somebody say no and tell me why. Because carboxylic acids are terminal. You only have one at each end. If there's one at each end, there's no place else you put in the middle because you have to have a hydrogen there. It has to end. So a carboxylic acid group always has to be terminal, has to be on the end. It can't be anywhere else in it. Okay. If it's going to be in there, it's going to involve what's called an ester because it has an R group. But this hydrogen has to be terminal because nothing else can bind to it. So if you got a carboxylic acid, you only have one at both ends, and that's it. You cannot have 3 of them. It's impossible.
So it can't be a substituent, like
Yeah, if it's a
attached to
sub-
one of the middle ones.
It sure can, but then it's not a 3. It's not a carboxyl. It's a carboxyl group. If it's
Okay.
it's called carboxyl because it's not on the main chain anymore.
I see what you're saying.
So
Okay.
there can only be dioic acid because you're naming the main chain. But that's a perfect question. If it occurred like off of here, like a COOH, then it'd be called a carboxyl group. Just like an OH group is a hydroxyl group, that'd be a carboxyl group. Okay. So you can only have 2 on the main chain because there's no other way to do it. Okay. So you can only have it to dioic acid. And then there's a bromine on number 3. So I put the name all together. It is 3-bromobutanoic acid. But that was a great point she brought out with just you can have a third one attached, but then it's not a carboxylic acid. It's a carboxyl group because a carboxylic acid has to have the carboxyl group basically on the main carbon chain. Perfect. Okay. Name that thing. How many carbons do we have?
2.
2. So you have 2 carbons. 2 carbons is ethane. Okay. It's a carboxylic acid, COOH. Okay. So we drop the E and add OIC acid. So it's ethanoic acid. There's no substituents, no other attachments. That's it. Okay. Ethanoic acid. Ethane is 2 carbons. Oic acid means there's a COOH group at the end. Okay. Another one. How many carbons on this one? 3 carbons, right? 3 carbons is propane. And it's got a COOH group, carboxylic acid. So we drop the E and add OIC. OIC, not OCI. A little dyslexic there. OIC acid, propanoic acid. Is there any substituents attached or anything else? Nope, just carbon and hydrogen. So that's it. So it's propanoic acid. Okay, now you're a little more complicated. So let's look at our chain. Look at our longest carbon chain, which is 1, 2, 3, 4. Okay. 4 carbons is butane. Okay. Again, functional group is carboxylic acid. So if we have a carboxylic acid, we drop the E and add OIC acid. So now we got butanoic acid. Now we have something attached to the chain. What do we have? What's that substituent group called?
Methyl group.
Perfect. It's a methyl group. It's 1 carbon. Okay. And it's attached to what number carbon?
3.
Perfect. So we have 3 methyl butanoic acid. Okay. And it tells you butanoic acid, 4 carbons, carboxylic acid, COOH. And at number 3 carbon, there's a methyl group attached. All right. That looks interesting. Okay. All right. So let's do our carbons. 1, 2, 3, 4, 5, 6 carbons in the chain. Does it matter if I start on the left side with number 1 or the right side with number 1?
Doesn't matter.
Perfect. Exactly right. Makes no difference. It's going to be the same numbers for our carboxyl either way because carboxyl groups are terminal. So we have 2 carboxylic acid groups. So you have 6 carbons. 6 carbons is hexane. So instead of hexane, we drop the E, hexane, and then we put in dioic acid because now we have 2. Okay, if there's 2 carboxylic acid groups, we have dioic acid. So hexane, dioic acid. And you get if it turns out where 2 consonants are together, they put the E back in to make it sound better because it'd be hard to pronounce hexane dioic acid. So hexane dioic acid. If there's 2 consonants, they'll put the E back in there. Okay, just so you can make this such what it sounds right. Because ND is a hard sound to make, but NED sound you can make. So hexane dioic acid, no substituents on top of that. Okay. Again, there's 3 carbons in your chain. So 3 carbons is propane. So we have drop the E. Well, actually, don't drop the E with this one. Propane dioic acid. Okay. So we keep the E in if there's 2 consonants between there. And I'm not, if you put propane if you don't put the E in there, it's not going to be marked wrong. You know, I'm not that picky, but it's just a matter of making it sound right. So they leave the E in there for the dioic acid. We do that a lot with other things also when the 2 consonants come together, make it hard to pronounce. All right. So that's propane dioic acid. So the di just means 2, oic acid, or carboxylic acid, 1 at each side, and the total of 3 carbons. Okay, polymers of lactic acid. Okay. We use polymers of that as biodegradable structures. What is the IUPAC name of lactic acid? Lactic acid looks like this. That's lactic acid. When we talked about that building up in muscles, did we talk about that last time? Or is that my other class? I think that's my other class. Build up lactic acid in the muscles. That's what, when you use your muscles, running long distances, working out, when you work out and you really work out hard, okay? You ever hear the expression hitting the wall? That's when your body stops working. And that's because the lactic acid is building up. What happens when your muscles start to work is they burn oxygen, they produce glucose, and break it down, produce ATP, and keep your muscle functioning. Okay. When you run, when the muscle is working so hard, you can't get enough oxygen. The body switches to anaerobic metabolism, which means it breaks down glucose without oxygen. One of the byproducts of breaking down glucose without oxygen is lactic acid. Lactic acid builds up, and when lactic acid builds up, all of a sudden it hits a level where you can't metabolize anymore, and your muscles stop, and you literally hit the wall. I don't, if you've run long distances and you've worked out extremely hard I used to run track and field as a pole vaulter, and we'd run certain hill workouts, and you'd run till you hit the wall, which means your body completely shut down, and you don't feel good, but it stops. I mean, your muscles will not contract anymore. The lactic acid has built to a point where it is shut down. And this is what does it. This is what causes your muscle cramps. This is what causes your body shut down. It's the buildup of this lactic acid inside those muscles. And then what's that?
Is that, I don't really know how to ask this. Is that when runners poop themselves?
Well, you lose control of bodily functions in other areas. If you're working out so fast, you can do that too. That's a byproduct of some of this. In other words, you lose control of your bodily functions because now you can't control your external sphincter muscles. Does that make sense? Because those are muscles. And if you depleted all your oxygen, all your glucose, because to have a muscle contract, it takes 2 things. You have to have calcium and you have to have ATP. If you depleted all the ATP, muscles don't contract, which means your external sphincter muscles can't contract, can't hold in your bowel movements, and can't hold in your urine. That's what happens. Your body just has to get rid of it, and you can't hold it because the muscles are not able to contract anymore. So yeah, that's part of it. That can very well be part of it. You're absolutely right. Did that answer your question?
Yeah, it did. I was like really curious about it because you were talking about how like your body hits a wall.
Right.
And I've seen like when people run super marathons, I guess you could call them, and then they are like, well, like they have control of their functions normally and are not incontinent, and then they end up like pushing themselves and become like incontinent during the race.
Right. That's because all the ATP that's being used to hold everything in, okay, is gone. That way the muscle can't contract anymore, so it opens up.
So why is hitting the wall different for every individual if it's just an oxygen intake?
Because everybody utilizes, because muscles have a special structure that absorbs oxygen called myoglobin. So now we're not dealing with hemoglobin anymore. Hemoglobin delivers oxygen to muscle. The more you work out and the better condition you're in, the more what's called fast twitch muscles or slow twitch store this myoglobin. The more you can store, the longer you can go for the individual. So the harder an individual works out, the more myoglobin that muscle can contain. So the more oxygen they can use before being depleted of the oxygen content in the muscle. It's not the oxygen content in the air. It's the oxygen content inside that muscle that's being stored. So the more in shape you are, the more myoglobin you have, the more oxygen that muscle can hold before you hit the wall. So that's why it's different for different people.
Is it kind of like if you, like the more you practice catch, like the better you are?
Oh yeah, definitely.
Okay.
Yep. The more you work out those muscles, the more myoglobin you're going to have, the longer they're going to last before they hit the wall. I mean, if I tried to race a 50-mile marathon against these people, I'd hit the wall about 2 miles right now. I mean, it's just not going to happen. Now I can bike ride 50 miles. So I can't run anymore. But yeah.
So those
more
people
you-
that have a large amount of myoglobin, and then like let's say they're very active, like in their 20s, and then not so much really in their 30s,
Right.
they start working out again in like their, let's say 40s, then that myoglobin, like are they starting over from scratch, or is it easier for them to get to where they were at because they were there once before?
It's easier to get there because not necessarily because the myoglobin content, because the psychological advantage to do that. Athletes that have worked out in their early years know what it's like to work out. They know what dedication takes, and they know how to push their bodies. Okay, if you're starting your workout for the first time in your 40s, you have no previous experience of how hard you push your body. Athletes who have worked out from high school through college and have pushed their bodies beyond what they can do, they understand the psychological aspect of training, and that's a big difference. That makes a huge difference. Okay, I'm not saying a 40, 50-year-old can't achieve that same goal. I'm saying psychologically, it takes a lot more for them to do it. Okay, because they're not used to that kind of training. They're not mentally conditioned. Because when you work out, your muscles start to hurt. They do. I mean, they start to burn. Okay, a lot of athletes can push through that because they know that feeling and they know what it's like to push through it. If you start later on, you got to learn that feeling. And as you're older, it takes a little bit more to get past those feelings. Okay. If you're never going to be in as good a shape. Well, I can't say that. You can get in good shape, but the potential for being in great shape is in your early 20s. Okay. As you get older, things change, but you still get in good condition, good shape. Does that make sense?
Yep.
Okay. There's a lot of factors involved. It's not just one thing. But this little guy, this lactic acid, that's what shuts you down. I mean, if you've ever hit the wall, it's a real feeling. I mean, you stop. It's physically like hitting a wall. You're not going to take one more step because muscles stop. Okay. So back to chemistry. Okay. What's the name of this thing? It's lactic acid. But let's name it. How many carbons in lactic acid?
3.
3.
3 carbons. And it's always number 1 at the carboxyl group, 1, 2, and 3. Now, so this is propane. That's our 3 carbons. Now we have a problem. We have 2 functional groups. We have a carboxylic acid and we have an alcohol. Okay. And what I said before is the functional group that is the most oxidized takes precedence. Okay. So the alcohol group has 1 oxygen. The carboxylic group has 2 oxygens. The OH group has 1 bond to oxygen. The carboxylic group has 3 bonds to oxygen. So there's more bonds to oxygen and there's more oxygen in the carboxylic acid. So the carboxylic acid is the most oxidized. So that is our functional group. How we're going to name it. So this is going to be propanoic. You can drop the E, add OIC acid. Okay. And this, instead of being an OL ending, this is going to be a hydroxy group. Okay. Just as we did before, if you had a carboxylic acid off the main chain, then it would be a carboxyl group. Okay. So in naming this, we have the number 2 position. We have 2 hydroxy propanoic acid. Okay. Do I ever have to put the number for the propanoic acid? Like, why don't I put 2 hydroxy 1 propanoic acid? Why don't I do that?
Because it always starts at 1.
It's always terminal. It always has to be number 1. You're exactly right. I mean, 2 people did that in sync, in harmony together. That was good. Both of you said it's got to be the number 1 because it's the number 1 carbon. It is terminal. So perfect. So you never put a number here to tell you where the carboxylic acid group is because you know it's in the number 1 position. It's always at the end. It has to be. Okay. So 2 hydroxy propanoic acid. That's lactic acid. That's what causes your muscles to ache and causes you to hurt when you work out. All right. The following compound is one of the monomers from which biodegradable plastic called Biopol is made. Name the carboxylic acid using the IUPAC nomenclature system. Biopol is one of the stuff that is biodegradable, and it's a fantastic thing to use in place of a lot of our bottles that are not biodegradable. So we have our carbons. We have 1 carbon. Again, it's always going to be at the end of the chain. 1, 2, 3, 4, 5 carbons. All right, 5 carbons is pentane. So we have pentane. Again, 2 functional groups. And like we said before, which one wins out? The carboxylic acid or the alcohol?
Carboxylic acid.
Carboxylic acid because it's more oxidized. Perfect. So pentane is the end. It's going to be carboxylic acid. Drop the E, add OIC acid. Okay. And at number 3, we have an OH group. So a hydroxy group. So we have 3 hydroxy pentanoic acid. That's bipol. That's a fully biodegradable substance. Okay. 3 hydroxy pentanoic acid. Okay. Name the following carboxylic acid with several examples here. It seems like you guys are catching on pretty quick to the naming carboxylic acids. All right. Count your carbons. There's a bunch of them here. We're always going to start where the carboxylic acid is, number 1. Then we'll have 2, 3, 4, 5, 6, 7, 8. Okay. So 8 carbons is octane. Okay, carboxylic acid functional group COOH. That's our carboxylic acid functional group. Okay, so we drop the E and add oic acid. Okay, and now we name our substituents that are part of that. We have 3 bromine groups at number 3, number 5, and number 7. So we have 3, 5, 7. Remember, there's commas between numbers. There's dashes between numbers and letters. So 3, 5, 7, tri, because there's 3 of them, bromo. And then octanoic acid. Okay, now we have 2 of the same vowels together. Most of the time, we're going to drop one of these because you can't say bromo octanoic acid. So it's bromo. Well, a lot of times they'll drop the O, but this one they'll leave it in place here for this one. Sometimes they'll change it depending on how it sounds. Like we said before with the E and stuff. But 3,5,7 tribromo octanoic acid. Just keep them together like that. Like I said, if you drop one of those O's, it would not be marked wrong. You'll see it written as different ways in different systems like that. But it tells you there's octanoic acid, this part right here, 8 carbons with a COOH group on the end. It says we have 3 bromines, 3 bromo at numbers 3, 5, and 7. So from the name, you can draw the compound. Okay. Determine the nature of each of the following structures. Now we're going to do backwards. No, we're not going to do it. We're going to name. We have to draw the structure eventually, but we're still going to name these things. So carboxylic acid, COOH, and again 1, 2, 3, 4, 5. 5 carbons is pentane. It's a carboxylic acid. Drop the E, add OIC acid, and we have 2 substituents attached. One is at number 4, and one is at number 2. Okay, and those are methyl groups. So we have 2, 4, where they're located, dash, dimethyl, because there's 2 of them, and this is pentanoic acid. Okay, so 2,4-dimethyl pentanoic acid. Okay. So you should have named most carboxylic acids by now. It's a straightforward naming system. Questions so far? Okay. All right, name this thing here. See, 11 people. Okay, perfect. So again, you recognize the functional group that's attached as a carboxylic acid, COOH. Carbonyl group and a hydroxyl group as a carboxylic acid. And then you number it, always starting with number 1 on the carbonyl carbon. 2, 3, 4. 4 carbons is butane. Okay, carboxylic acid, we drop the E, add OIC acid. And now we have 2 substituents or 2 attachments to that chain. One's at number 2, one's at number 4. So now we name it. We have 2, 4, and we have 2 of them. So it's di and it's chlorine group. So dichloro, and we add our butanoic acid. Okay. 2,4-dichlorobutanoic acid. Okay. Again, looking at the name, we break it down from the end. Butanoic acid. We have 4 carbons, carboxylic acid at the end. We have 2 chlorine groups. One's at number 2, and one's at number 4. Okay. Now, again, we have functional groups. We have a carboxylic acid group here, and we have hydroxyl group and hydroxyl group. Again, the most oxidized is a carboxylic acid. So that's how we're going to name it. So the other one's going to be as attachment. So 1, 2, 3, 4. Again, that's butane. And it's a carboxylic acid. Okay, so we drop the E, add OIC acid. And there's groups at 2 and 3. What do we call an OH group when it's an attachment and not an alcohol? When it's an alcohol, we put an OL at the end. When it's a substituent, we call it what?
Hydroxy.
Perfect, hydroxy group. Okay, so we have 2 and we have 3. And we have dihydroxy. Those are 2 hydroxy groups attached. Butanoic acid. And put the end of it on. Okay. 2,3-dihydroxy butanoic acid. So breaking it down, we have butanoic acid, 4 carbons, carboxylic acid, COOH at the end. And then we have 2 hydroxy groups, OH at 2 and 3. Okay, I think this is one more be the last example, then we'll start doing the other way around. All right, so we're looking at this. We have carboxylic acid, and we have 1, 2, 3, 4, 5, 6 carbons. All right, 6 carbons is hexane. It is a carboxylic acid. So we drop the E, add OIC, oic acid. Drop the E, add OIC, that's an O, acid. And now, that's the main chain. We look at our substituents, our attachments. We have 1 there, 1 there, and 1 there. And they're all different. So we have at number 2, what do we have?
Bromine.
Bromine. So we have 2 bromo. At number 3, what do we have?
Chloro.
Chloro groups. At number 4, what do we have?
Methyl.
Methyl group. And we put those in alphabetical order, right? So we have 2 bromo, 3 chloro, 4 methyl, hexanoic acid. Putting them together. So 2 bromo, 3 chloro, 4 methyl, hexanoic acid. Okay. And that's what we have. You can always double check your work. Going back and like I said, working backwards. Hexanoic acid is 6 carbons. Okay, carboxylic acid, the OH group on the end. At number 4, we have a methyl group, which is right here. At number 3, we have a chlorine group, which is right here. And number 2, we have a bromine group, which is right there. And that's how you name it.
Does capitalization ever matter?
In organic chemistry, we don't usually use capitals. Everything's usually lowercase. The reason for the IUPAC system is so you can enter a compound with a typewriter. In the old, when we had typewriters before computers. So it was just easier not to capitalize anything. So
Okay.
yes, I don't think they usually use a capital for anything organic chemistry. It's just easier that way when they typed it.
Just know.
All right. Okay, carboxylic acid derivatives of cycloalkanes are named by adding the suffix carboxylic acid to the name of the cycloalkane or the substituted cycloalkane. Remember, cycloalkanes are ring structures now. And we're going to add those at the name. At the number 1 position is going to be our carboxylic acid group. So the carboxyl group is always carbon number 1, like always. So our C double bond O group, it's always going to be number 1. And the other substituents are named and numbered to give them the lowest possible number, just like we normally would. Okay, so here's our cyclical or cycloalkane. There's 1, 2, 3, 4, 5, 6 carbons. Okay. Okay, the number 1 carbon is always attached to the carbonyl carbon. That's going to be number 1 in the ring structure. Okay. So this is going to be what's 6 carbons in a cyclical ring. It's cyclohexane. Okay. Okay, we use the same rules we did before. Okay, cyclohexane carboxylic acid. So we're not going to put an oic acid. We're going to call it cyclohexane, and then attached is going to be
Look at Steve's office. Look at this.
carboxylic acid. Okay, so
I know.
all right, so we got cyclohexane,
I know.
carboxylic acid. It gives you your name, the ring structure, and then you name the carboxylic acid. Okay. Okay. Determine the impact name for each of the following structures. So we have got our cyclical compound again, and attachment off of it. So this is a carboxylic acid. Remember, carboxylic acid is abbreviated COOH because this is COOH. Okay. So a ring structure, there's 6 carbons around the ring. So it is a cyclohexane. Okay. And the attachments are going to give the substituent right here the lowest possible number. So we're going to number it clockwise. If we numbered it counterclockwise, we'd have 1, 2, 3, 4. The substituent would be at number 5. We number it clockwise, the substituent is number 3. So this is a cyclohexane carboxylic acid, and with a number attachment of a methyl group at number 3. So it would be 3 methyl cyclohexane carboxylic acid. There's a C there. Okay, you can see a little bit here. So 3 methyl cyclohexane carboxylic acid. Okay, again, you never have to put the number where the carboxylic acid is because it's always going to be the number 1 position on the chain by definition. So 3 methyl cyclohexane carboxylic acid. You're naming the 3 components there. Okay, it's just a little bit different when you're doing cycloalkanes or cyclohexanes. Again, COOH is a carboxylic acid, and we have 1 attachment on the ring. So the rings are numbered. So the number 1 carbon is always where the carbon of the carbonyl group of the carboxylic acid is attached. And then we're going to go either counterclockwise or clockwise to give any other substituent the lowest possible numbers. So this we're going to go clockwise, 2, 3, 4, and 5. So it's a 5 carbon cyclical ring. Okay, 5 carbons is pentane.
It's break
So
time.
it's about 10 minutes.
Yeah.
It will be. Then we'll have something to eat. Cyclopentane. Okay. Again, the number 1 carbon is always going to be at the carboxylic acid. And number 2, what's the attachment group we have in the number 2 position here?
Ethyl group.
Ethyl group, perfect. So we've got 2 ethyl. Okay. 2 ethyl cyclopentane. Left with our carboxylic acid. Okay. Oh, I put it right in there. I thought I was being good by writing it not in the right spot, but I ended up putting it right over it. Get rid of some so you can see a little bit better here. Get rid of some of the words, some of the letters. There we go. All right. So you can see it's a carboxylic acid, which is our COOH group. It's a cyclopentane, 5 carbon ring. Okay. And at the number 2 position, there is an ethyl group. So 2 ethyl cyclopentane carboxylic acid. Okay. Write the structure. Now we're going to draw the structure. We're going to do a little bit backwards, and we'll get a break in about 10 minutes or so. We'll take about a 15-minute break. 1,4-cyclohexane dicarboxylic acid. That's a mouthful. Okay. So what did I tell you? You always work which way when you see an organic chemistry name. You work backwards, right? Okay. So dicarboxylic acid. There's two carboxylic acid groups. So there's going to be two COOH groups. It's going to be a cyclohexane. So it's going to be 6 carbons. 2, 3, 4, 5, 6 in a ring structure. There's going to be 6 carbons. Okay. And we're going to have 2 carboxylic acid groups. Where are they going to be? Well, it says it's at number 1 and at number 4. So 1,4 cyclohexane dicarboxylic acid. And that's what it's going to look like. And I should have put it to the side. So you can see this a little bit better. Okay. Again, by definition, you got number 1 carbon, and then 2, 3, 4, 5, and 6. So cyclohexane. So dicarboxylic acid means there's 2 carboxylic acid groups. And one has to be at number 1. The other one is going to be at number 4 because it says so in here, and that's where you put it. So 1,4 cyclohexane dicarboxylic acid. Okay. 4-hydroxy cyclohexane carboxylic acid. Okay. Again, so it's a carboxylic acid. So you know there's going to be a COOH group. That's your carboxylic acid. And this is a cyclohexane, which means 6 carbons in a ring structure. Okay, so there's your cyclohexane, and then carboxylic acid. We can put it any position. Is number 1 position. Okay, so there's cyclohexane carboxylic acid. At number 4 position, there's going to be hydroxy group. Hydroxy is OH, the alcohol functional group. So that's 1, 2, 3, and the number 4 position is right there. So 4-hydroxy cyclohexane with a carboxylic acid. Again, by definition, it's attached to the number 1. The carbon that the carboxylic acid is attached to is the number 1 position. Then all the other constituents get named according to that. Common names. Right? We use Greek or Latin prefixes. The suffix is ic acid rather than oic acid when you're in the common name. And Greek letters indicate the position. Remember, we had alpha, beta, gamma, delta, epsilon, and so on. For the Greek letters, it showed position of the substituents. So what I need you to know, just like last time, I'm not really interested in the naming of these things in common names, but I need you to know that the alpha carbon is the one adjacent to the carbonyl carbon. The carbonyl carbon itself is not named in common names. You have an alpha, beta, gamma, delta, epsilon, and so on of the Greek alphabet. Okay, so the first carbon, the alpha carbon, is not the carbonyl carbon. Okay, it's the carbon adjacent to it. That's where we start our alpha, beta, gamma, deltas, etc. Okay, so for this compound here, there's the alpha carbon, beta, and gamma. So this would be beta hydroxy. Okay, so this would be beta hydroxy butyric acid, or what our name would be 3-hydroxybutanoic acid, according to the IUPAC nomenclature. I don't need to worry about these. I'm not going to be testing you on these names, but you will see on the exam the alpha carbon, beta, so on. So you need to know how we number with the Greek letters. Okay, that we're not including the carbonyl carbon with this one. We do include it in the IUPAC name. It is number 1 carbon. Okay. And again, this would be 2-hydroxy propanoic acid. And the alpha carbon would be this one right here, and then the beta carbon. Go 2-hydroxy propanoic acid. or alpha hydroxypropanoic acid. So this is the different names of the different types of acids, the chemical structure, see how many carbons are in it, and then the source of where they get it from. Like formic acid we talked about, methanoic acid with just one carbon. We talked about that, and that's what gives ants. When the ants bite out here, they give you that sting and that burn. That's the methanoic acid. Ethanoic acid is vinegar. Propanoic acid is Swiss cheese. And butyric acid is that rancid butter, that gangrene smell. And that's just terrible. As it gets better, though, as it gets longer carbon hydrogen chains, it starts to turn into a more pleasant smell like palm oil, okay, etc. Okay, it doesn't have that rancid smell anymore as they get larger. It's a small molecular weight carboxylic acids that have that really bad smell. Okay. Now we've got benzene also. Benzoic acid derivatives. Remember, benzoic acid is a benzene ring with a carboxylic acid group attached to it. And then we can name things off of that. Remember, it's not a cyclical group, it's a benzene group. It is a conjugated double bond system. So you see it represented by a circle, or most likely you'll see it represented like that, where all the double bonds are a hybrid. Every double bond's the same. That's what the circle indicates. Okay. But every other bond's a double bond. And those are the ones that smell real nice. So we have benzoic acid, benzene ring with a COOH attached. That's benzoic acid. This is always going to be the number one position where the carboxylic acid group is attached to it. Remember meta, ortho, and para. Ortho, meta, and para. Ortho was in the number 2 carbon. Meta was the number 3 carbon. And para, where's para? Oh, we don't have a para on here. Para is in the number 4 position. Okay, so this compound right here, it's meta toileic acid, or how I'd want you to know it is meta methyl benzoic acid. That's how I expect you to know it. Okay, so meta methyl benzoic acid. Okay, remember this is ortho, meta, and para, or 3 methyl benzoic acid. Same thing. Okay, this is number 3 carbon, and it's a methyl group. And then you have benzoic acid. So here's your benzoic acid attached to the benzene ring. At the meta position, you have a methyl group. So M-methyl benzoic acid, or 3-methyl benzoic acid. Okay, ortho-bromo benzoic acid. Okay, or 2-bromo benzoic acid. Same thing. Remember, ortho is at the number 2 position, meta is the number 3 position, para is the number 4 position. Okay. Okay, and we down here we have meta iodo benzoic acid, or 3-iodo benzoic acid, because this is number 1. That would be 2, that would be 3. Okay, it's in the meta position. So meta iodo benzoic acid, or 3-iodo benzoic acid. Okay, phthalic acid, okay, would be what? There's 2 carboxylic acid groups. Okay, so it'd be 1,2-di-benzoic acid. Because there's 2 carboxylic groups attached to that one, and it's at the 1 and 2 positions. So 1,2-benzoic, 1,2-di-benzoic acid. Okay, and that's how we name our benzene groups. So naming carboxylic acid attached to a benzene ring. Benzoic acid is the simplest aromatic carboxylic acid. Remember, benzene is a very pleasant smelling compound. And that's why it's used in a lot of cleaning solutions. And it was used a lot in the 1960s until they found out all the janitors were dying of liver cancer from it. Benzene is extremely carcinogenic. If we use it in the lab, use it in a hood, because you don't want to breathe that stuff in. And this is benzoic acid. Your benzene ring, alternating double bond, six carbon ring with a carboxylic acid group attached. That's benzoic acid. And everything is a derivative of that. Okay. So here we would have, this is always number one. So we have 3-methyl. And then this is benzoic acid. Or ortho-meta. Or meta-methyl benzoic acid. Remember, with benzene, we can use ortho, meta, or para at those positions. Okay, so 3-methyl benzoic acid or meta-methyl benzoic acid. It tells you benzoic acid is a benzene ring with a COOH group in number 1 position, and the 3rd carbon there is a methyl group. Okay. Again, benzene ring with a carboxylic acid group attached to it. Okay, that would give you, here's your carboxylic acid group. So this is benzoic acid, and then attached to it is a bromine. What number carbon is a bromine attached to?
2.
2, perfect, you got it. So it'd be 2, right up here so it doesn't get in the way of the compound. 2 bromo benzoic acid. Instead of writing 2, I could write O bromo benzoic acid. Okay. Now you can only use ortho, meta, and para with a benzene ring. You can't use it with just this regular cycloalkane. Okay, it has to be a benzene ring. That's where you get the nomenclature of the ortho, meta, and para from. So 2-bromobenzoic acid or ortho bromobenzoic acid. Okay, again, carboxylic acid, benzene ring. We've got benzoic acid, and we have an iodine attached, and that is at number. If the carboxylic acid group is number 1, the iodine is at number 3. So 3 iodo benzoic acid or meta iodo benzoic acid. Okay, so 3-iodo benzoic acid or meta iodo benzoic acid. Either way, it's the same compound. Okay. And then the dicarboxylic acids that we named. Okay, that would be 2-carboxy benzoic acid. So this means there's a carboxy group on this one. So here's your benzoic acid, and then you have a carboxy attachment to it, and that's at the number 2 position. So 2-carboxy benzoic acid, or ortho carboxy benzoic acid, because there's another carboxyl group at the ortho position, at the number 2 position. So remember, OH groups are, if they're not the main substituent for the function group, they're hydroxy. Carboxylic acids are carboxy, if they're not on the main chain, if they're a substituent attachment. Okay. Phenyl group is benzene with 1 hydrogen removed. Remember, when benzene's attached, okay, if it's attached to an OH, it's a phenol. If it's attached as a substituent to something else, it's phenyl. So when benzene's attached as a substituent group, like this is your carbon chain, if you have a benzene ring attached as a substituent and not part of your main group, then it's called a phenyl group. Right? So it's benzene with 1 hydrogen removed because that's where the bond occurs. Okay. So the phenyl group is benzene with 1 hydrogen removed. The alkyl group, often the group is treated as a substituent. Okay. So when benzene's at a substituent, you take a hydrogen off, and that bond that was to hydrogen now attaches to the carbon chain, making it a substituent. We'll give you an example here. Okay, so here we have a CH2 group, then we have our COOH, the carboxylic acid group. Okay, so now it's not benzoic acid anymore because there's a carbon in between there. So now we got to name this compound and put this as a substituent. Okay, so we have 2 carbons, 1 and 2. That's our main chain. So that's ethane, right? 2 carbons is ethane. Okay, it's a carboxylic acid. We drop the E, add oleic acid. And at number 2 carbon, we have an extension, an attachment to it. Okay, substituent group, 2-phenyl. Okay, remember benzene ring is called phenyl when it attaches to the main chain. So the name for this would be 2-phenyl ethanoic acid. Okay, I'm going to get rid of that because it's going to get in the way of the next one. Okay, is that making sense now? If the COOH is attached directly to the benzene ring, then it's benzoic acid. We name it according to that. If it's attached, if the benzene ring is attached as a substituent, okay, it's named as a phenyl group, and I put what number it's attached to. So this is a 2 carbon, right here. This is a 2 carbon carboxylic acid. At the number 2 carbon, there's a benzene ring attached. So it's 2-phenyl. That tells you it's a benzene ring. Ethanoic acid tells you it's 2 carbons and a carboxylic acid. Okay. How about this one? Again, here's our longest chain. With our COOH group attached, our carboxylic acid group. And there's 3 carbons. 1, 2, 3. Okay, so 3 carbons is propane. Carboxylic acid, drop the E, add oleic acid. And at number 3, there's a benzene group. And benzene groups as substituents are called phenols. So we have an attachment number 3 of a phenyl group. So we got 3-phenyl propanoic acid. Again, propanoic acid here, it tells you 3 carbons with a COOH group at the end. Then it tells you at the number 3 position, there is a phenyl group. And that's a compound. Okay, name the following IUPAC names. Okay, the COOH group is attached directly to a benzene ring. Okay, so this is benzoic acid. Okay, benzoic acid. And we have an attachment. Okay, at what number carbon is our attachment?
Four.
Number 4, perfect. That's at number 4. And it's a chloro group. So 4-chloro benzoic acid. If I didn't want to put 4, what else could I put since that's a benzene ring? Would it be ortho, meta, or para?
Para.
Para. So I could put P-chloro. Either one of those would be fine. So it's 4-chloro benzoic acid or para-chloro benzoic acid. Okay. So at the 4 position or at the para position, it's the same thing as long as you have that benzene ring. You can use that nomenclature. So benzoic acid is a benzene ring with a COOH group directly attached and a chlorine at number 4 position or at the para position. Okay. All right. Is the COOH group directly attached to the benzene ring? No, right? So it is not benzoic acid. So we have to name our longest chain. Okay, our longest chain is this right here. So how many carbons in our longest chain? 1, 2, 3, 4, 5. Okay, just because they're written out, there's still a continuous chain there. So 5 carbon chain is pentane. Now carboxylic acid, because COOH, you drop the E, add oic acid. And at the number 4 carbon, we have a substituent group. We have a benzene ring, which is called phenol. So at number 4, we have phenol. Okay. Now, could I put orthometa, because a 4-phenol is a para, right? Could I put para, phenol, pentanoic acid? Someone say no, and then tell me why. Can't do that, right? Because it's not on the benzene ring. Orthometa and para only apply when it's the 1,2, 1,3, 1,4 relationship on the benzene ring. Okay, those are not attached to the benzene ring. It's just a normal attachment. So the name of his compound is 4-phenol pentanoic acid. Okay, that's the only one it can be. You cannot use orthometa and para because they're not attached to the benzene ring itself. Does that make sense? They're attached to the long chain hydrocarbon here. It's not attached to the benzene ring.
Professor?
Yep.
What are the Greek prefixes again?
The Greek prefix, it would start here. This would be alpha. This would be beta. This would be gamma. This would be delta. And that would be, the next one would be an epsilon. If it came across there. Remember that when we do the Greek prefixes, it starts at the carbon adjacent to the carbonyl carbon. The alpha is not the number 1 carbon. Alpha is our first one in the Greek alphabet, but it's the one adjacent to the carbonyl carbon. That's the difference between the numbering systems.
Okay, and what was after delta, sorry.
Alpha, beta, delta, alpha, beta, gamma, delta, epsilon. We won't go past that.
Okay.
And epsilon looks kind of funny, but epsilon's written like that. That's epsilon. Okay, perfect. Draw structures. All right, let's draw the structures. Ortho, methyl, benzoic acid. Again, always just work backwards. Just makes life so much easier. Benzoic acid. Benzoic acid is a benzene ring with what attached to it?
Methyl.
Not methyl. Well, yeah, there is a methyl group attached to it. But benzoic acid is a benzene ring with. So, but to draw benzoic.
COOH.
Perfect. That's exactly what I was looking for. You're right. So you draw a benzene ring, and then you attach a CO, and you attach it anywhere. But we can attach it at the top, make it easy. COOH. That's benzoic acid. Then it tells you there's a methyl group attached at the ortho position. So ortho, meta, and para apply to the benzene ring itself. So it's attached directly to the benzene ring at the ortho position. Ortho is a number 2 carbon. Ortho's 2, meta's 3, para's 4. So the methyl group attached at the number 2 position. So that's orthomethylbenzene or 2-methylbenzene. Okay. And that's what it looks like. This is benzoic acid right here. As long as the COOH group, the carboxyl group, is attached directly to the benzene ring, now we got benzoic acid, and everything else is named as a substituent. If the COOH is not, the carboxyl group is not attached directly to the benzene ring, then the benzene ring is a substituent and is named as a phenol. Okay. 2,4,6 tribromobenzoic acid. So again, working backwards. Benzoic acid, draw that. Benzoic acid is a benzene ring. Okay, with COOH attached to it. And I just put it on top because it makes it convenient. You can put it anywhere you want, but where you put it is gonna be the number 1 position. And then you count from there. We have the number 2 position. We have number 4 position and number 6 position. And they're all bromines, tribromo, 3 bromines. Bromine, bromine, bromine. So we have 2, 4, and 6 tribromo, 3 bromines at those positions, and benzoic acid. Okay, and that's what it looked like. You have a benzoic acid core, and then you have 3 substituents and 3 attachments. And it tells you there are 3 bromine molecules, and they're at 2, 4, and 6. Ooh, that's gonna be an interesting one. 2,2,2 triphenyl ethanoic acid. That's gonna be a lot of drawing. All right. Again, always just do yourself a favor, work backwards. Just makes it so much easier. Ethanoic acid. Ethanoic acid tells you what? It tells you how many carbons, and it tells you the functional group. So how many carbons does it have?
2.
2.
2, perfect. And what's the functional group? What's oic acid? That means it's a
Carboxyl.
carboxyl, carboxylic acid. Perfect. So you have 2 carbons, 1, 2, and you have a carboxyl group, carbonyl carbon and an OH, carboxylic acid. Okay. And it says, so that's your ethanoic acid, and then you have 2, 2, 2 triphenyl. You have 3 phenyl groups attached to the number 2 carbon. So if there's 1 phenyl group, there's 2 phenyl groups. I'm not the best artist here. And there's 3 phenyl groups. Okay. So you have 2, 2, 2 triphenyl ethanoic acid. That's what it looks like. Here's your main carbon chain, ethanoic acid. And then the benzene group is a substituent. It's an attachment because the carboxyl group, the COOH, is not directly attached to the benzene ring. If it was, then it would be a benzoic acid. If it's not, then the benzene ring is named as a substituent, as an attachment. So it tells you there's 3 phenyl groups that are attachments, each one the number 2 position, and the main carbon chain is 2 carbons long. Okay, makes sense. I know it looks kind of funny. Does that make sense though?
So putting a circle in the middle is the same thing as just doing these 3 lines, right?
Correct.
Okay.
You'll see it represented both ways.
Okay.
Yep. P or para-methyl benzoic acid. Again, work backwards, benzoic acid. Benzoic acid means you have a benzene ring with the carboxylic acid attached to the benzene ring, and that is always the number 1 position. So let's put benzoic acid. There's your benzene ring. And let's put our carboxylic acid right here. Not to the top this time. Okay. So there's our benzoic acid. And it says P-methyl, means para-methyl. So what's the number I would put instead of P? What number is attachment on the ring?
4.
Number 4, perfect. Okay, you can put 4-methyl benzoic acid or P-methyl benzoic acid. So this is your ortho, your meta, and here's your para. And that's the methyl group. Okay. Oops, dropped him. Okay. Like I said, you put the COH group anywhere you want on the ring. That's the number one position. And then from there you count. This is number 1, 2, 3, 4. This is ortho. This is meta. This is para. Okay. 3-phenyl hexanoic acid. Hexanoic acid is 6 carbons. So put 6 carbons. 1, 2, 3. Where am I at? 1, 2, 3, 4, 5, 6 carbons. COOH. Okay, so it's hexanoic acid. At the number 3 carbon, there's a phenyl group. So 1, 2, 3. The other ones are CH2, CH, CH2, and a phenyl attachment right here. Okay, so it's 3-phenyl hexanoic acid. Whenever you see phenyl, you know your benzene ring is a substituent. And it's attached to the number 3 position of the longest chain carbon, the longest chain carbon. Okay. So if you want to look at that, that's 6 carbons, 1, 2, 3, 4, 5, 6. And again, at the number 3 carbon, there is a phenyl group. Okay. The phenyl group is not directly attached to the carboxyl group. Therefore, it's a substituent. If it was attached directly to it, it would be a benzoic acid. Okay. Holy cow, that's a long one. 3-phenylcyclohexane carboxylic acid. So, like I said, work backwards and break it down. Okay. Carboxylic acid is the ending of it, right? So we know it's going to have a COOH group. And it's going to be a cyclohexane. Cyclohexane is a cyclical compound with 6 carbons all attached to each other. So 6 carbons all attached. It's just like our benzene ring, except there's no double bonds now. Okay. So it's a cyclohexane carboxylic acid. So we're going to put our carboxylic acid attachment to our cyclohexane. And at the number 3 position, there's going to be a phenyl attachment, which is the benzene ring. So the number 3 position, we have a benzene ring. Okay. Could we have called that meta-phenyl cyclohexane carboxylic acid? And got the same picture. Someone say no and tell me why.
Because that only applies to benzoic acids.
For the benzene ring, you're exactly right. Perfect. That only applies when it's on a benzene ring. The benzene ring is a substituent, it's not the main grouping. This here is not benzene. This is cyclohexane. Okay. Only benzene can have ortho, meta, and para attachments, not cyclohexane. You both have 6 carbons in a cyclical compound. Okay, but it has to have that conjugated double bond system. Right? So you cannot use ortho, meta, and para unless you're referring directly to a benzene ring. Exactly right. Perfect. Okay, but here we have 3-phenyl cyclohexane carboxylic acid. So cyclohexane carboxylic acid, and then number 3 position is a benzene ring attached to it. That's your phenyl group. Okay, so that's what it looks like. Let me get some of that out of the way here. So you can see a little bit better. There we go. All right. So this is your carboxylic acid. This is your cyclohexane. And this is your phenyl group attached to the number 3 position. Because by definition, where the COOH group attaches to any cyclical structure, it is a number 1 position. Okay. So 3-phenyl. cyclohexane, carboxylic acid. And that's how we name cyclical carboxylic acids. Okay, so far so good. Any questions? All right, some important carboxylic acids that we're dealing with. C3, 16 CH2s, COOH. Okay, that's a total of 18 carbons. Okay, that's stearic acid. That's beef fat. That's what you get in ribeyes, prime rib. That's beef fat. Okay, that is octadecanoic acid. I think deca is 10, octa is 8, so that's 18 carbons. So octadecanoic acid. That's beef fat, your stearic acid. Okay, this one here. This is dicarboxylic acid, and it's citric acid. That's what gives citrus fruit its flavor, its smell. Okay. You can see there's actually 3 carboxylic acid groups attached and 1 OH group. Okay, so this would be 1, 2, 3, 4, 5 carbons. So pentane dioic acid, and then at the number 3 carbon, there's a carboxyl group and a hydroxy group. So 3 hydroxy, 3 carboxy, or I'm sorry, 3 carboxy, 3 hydroxy, pentane dioic acid would be the name for this thing. Well, the same rules we've been following, because it's 1, 2, 3, like I said, it's 5 carbons. We'll put it over here to the side. So 5 carbons is pentane. Okay, when there's 2 of them, it's pentane dioic acid. Okay, and at number 3, there is a hydroxy group and a carboxyl group. So 3 carboxy, 3 hydroxy, pentane dioic acid. Okay, that brings back to that group why you can't have a tricarboxylic acid. You only have di, because after 2, the COH group has to be named as an extension or as an attachment. Okay, so Tanana would be 3 carboxy, 3 hydroxy, pentane dioic acid. Again, that's citrus fruit because you have smell. Okay, we should be able to name this one by the IUPAC name, not the common name. But there's 3 carbons. Okay, so there's 3 carbons. It's going to be propane. Okay, there's 1 carboxylic acid group. Drop the E, add oic acid. And at the number 2 carbon, there is a hydroxy. Okay, so to name that would be 2 hydroxy propanoic acid. Okay, it's called lactic acid, found in yogurt. Okay, and that's also what builds up in the body that causes your muscles to stop working. Okay, when you do anaerobic metabolism, when the body muscles are used without the presence of oxygen, and you get the breakdown. One of the breakdown products is lactic acid. Okay, and this is one of our sugars. So how's this one named? How many carbons? 1, 2, 3, 4, 5, 6 carbons. So 6 carbons is hexane. And there's 2 carboxylic acids. So dioic acid. Okay. When you see the di, you know COH is at both ends because they're terminal. So it's hexane. It's just hexane dioic acid. 6 carbons, a carboxylic acid group at each end. Okay. It's also called adaptic acid. This is beet juice. adipic acid is your beet juice, or it's hexane dioic acid is the IUPAC name for it. Okay. Like we said before, the stinging sensation of an ant bite is caused by methanoic acid. That's what causes it to burn. Okay. Acid taste of vinegar is ethanoic acid. Okay. Acetic acid. Propanoic acid, what we just did. Propanoic acid is a product of bacterial formation of milk. Okay. Most notable is a tangy component in the characteristic flavor of Swiss cheese. It gives Swiss cheese its smell, distinct smell. Butanoic acid we talked about. The odor associated with rancid butter and gangrene. Okay. Contribute to carotid smell of necrotic tissue. Necrotic tissue, if you worked in an ER room, if you ever worked out a patient come in, you can smell that patient before they get into your waiting room. Necrotic tissue has a very, very distinct smell. You ever watch the CSI shows and they go to the front door and they sniff and they know the dead body's in there? That's absolutely true. You can smell it from the sidewalk. Okay, necrotic tissue has a very distinctive odor. Okay, that's your butanoic acid. And that's the same product we use, this butyric acid, butanoic acid, that we're going to use to turn genes on for sickle cell anemia and for beta thalassemia. Okay, that's the one that's going to associate it with turning the gene on for fetal hemoglobin. So you can make the hemoglobin without using the beta chain, which is the defective chain in sickle cell anemia and beta thalassemia, which can both be fatal diseases and now can be treated with a simple carboxylic acid injection. Or we're working towards that direction. The research is looking really good. So these foul-smelling carboxylic acids have a far more pleasant potential. And we're going to explore that potential right now. When carboxylic acid react with alcohols, the products are what's called esters. Okay, now we got esters. They contribute to the fragrance and flavor of many fruits. Esters smell nice. Carboxylic acids stink. Okay, we create esters by reacting a carboxylic acid with an alcohol. Okay, an ester is going to have the form, and we'll go over this in a lot of detail right now. R, C, there's your carboxyl group, there's your oxygen. Now, a carboxylic acid would have a hydrogen there. An ester is going to have an R group here, another carbon group. Okay, that's an ester. Just by replacing a hydrogen in the carbon group, you make it smell a whole lot better. Okay, octanic acid has an inner function for human appetite. Why do certain people keep eating when they shouldn't? I mean, certain people can sit at an egg and eat for hours. Okay, there's something in the body that does that, that triggers your hunger response. Okay, it's called the hormone ghrelin. Ghrelin produced in the stomach is something called the hunger hormone. Okay, it stimulates, okay, the hypothalamus of the brain to signal the body that it's hungry. The hypothalamus, I think we talked about in the last class in human anatomy, but the hypothalamus is your thermostat. Just like you walk in a room and you adjust the heat and something, that's what the hypothalamus does in your brain. It says the body's cold, so it shivers, produces more muscles, releases heat. It modulates your body. That's what regulates everything in the body. Your food intake, your oxygen, how deep you breathe, how you breathe when you're sleeping, okay, how much oxygen your body needs. Everything's regulated by this hypothalamus. That's your body's thermostat. That also signals the body when you're hungry. So it releases a hormone called ghrelin. Okay, hormone is not the hormone alone does not have this effect. Okay, ghrelin must be covalently bonded to a molecule of octanoic acid. Octanoic acid, we can draw that compound, right? Octanoic acid is octane, 8 carbons, okay, and add a COOH group on the end of it. So in order to have the hunger stimulating effect on the hypothalamus, this ghrelin compound that's produced has to bond to octanoic acid. So if you cut out products in the diet that contain octanoic acid, you are effectively going to reduce the hunger hormone. And they're not going to keep eating as much. If you eat foods high in octanoic acid, guess what's going to happen? You can figure this out, right? Octanoic acid is going to bond to the ghrelin, and you're going to say, "Oh, I am hungry," and you'll see that all the time, just in your own experience. Have you ever just eaten something, all of a sudden you go, "You know, I just had lunch, but I'm really hungry." Depends how much content of octanoic acid is in there and bonding to this ghrelin that's produced. Okay, so fatty acids, okay, are these long chain monocarboxylic acids and can be isolated from a variety of sources like palm oil, coconut oil, buttermilk, lard, and animal fat. Okay, fatty acids forms triglycerides. That's what builds up in the bloodstream. They're the major energy storage form in mammals and in many plants. That's how we store energy, is these triglycerides. Okay, so when the fatty acid triglycerides saturated, the result is a solid fat like an animal fat. Okay, when they're saturated, saturated means the maximum amount of hydrogens, which means there's no double bonds. Okay, if there's a double bond, it's unsaturated. Okay, remember, because you always add hydrogen by hydrogenation across a double bond and increase the amount of hydrogens. So anything that has no double bonds, all single bonds, is a saturated, okay, hydrocarbon. Okay, when they're saturated, okay, you have a solid fat. When you have unsaturated fats, which are healthier fats, they're your oils. They're not fats. They stay as liquids in the body. They don't clog your blood. They don't clog the vessels on things like that. Okay, when you have the solid fats, that's where things clog up and cause problems. Because when it's saturated, okay, all you got these long chain hydrocarbons. Remember we talked about London dispersion forces. So if I have, okay, that's a saturated hydrocarbon. There's no double bonds. So if you have another hydrocarbon, it can line up. And then you have these attractive forces that line up because of temporary dipoles. We talked about London dispersion forces before that help hold it. Not as strong as hydrogen bonds, but they do tend to hold things together, so they make it a solid fat. If you throw a double bond in there, okay, now what's going to happen? Okay, these hydrocarbons don't line up the same anymore, so you don't get this dispersion force attraction, these London forces anymore, because now you've broken the continuity of the chain, and they don't stack nice and neat together. So you don't get them sticking together. So they're liquids. Okay. It doesn't take as much force for them to break apart because there's not much holding them together anymore. So the saturated hydrocarbons are the ones that are deadly, the ones that you want to avoid, because that forms fat in your body, in the bloodstream. The unsaturated ones don't stick as well. Okay. So when the fatty acids are unsaturated, okay, they're a liquid like olive oil, canola oil. Okay. Those are the healthier fats for you because they are unsaturated. They're going to form liquids in your blood, and they're not going to clog. They're not going to cause arteriosclerosis. We'll get some of this out of the way so you can read my writing. I forgot I was going to put terms underneath there. There we go. Perfect. Okay. So fatty acids, triglycerides, okay, saturated, those are your solid fats. Unsaturated fatty acids are your liquid fats, olive oil, canola, that are healthy for you when you cook and eat. Okay. The more complex carboxylic acids are found in a variety of foods. Citric acid is found in citrus fruits, often used to give that sharp taste of sour candies. Okay. That famous sour taste that everybody loves. Okay. It also stores a preservative, like an antioxidant. Adaptic acid, hexane dioic acid. Okay, 6 carbons, COOH group at each end. That gives you the tartness to soft drinks and helps decrease spoilage, helps preserve foods. Bacteria in milk produce lactic acid by fermentation of the sugars in milk. Milk has a lot of sugar. If you have a child, you never put that baby to bed with milk in the bottle, ever. If you do, we end up with what's called grenade mouth. I come in my office and all the teeth will be black. And you get to like a baby denture because all the teeth will be destroyed. Milk is extremely high in sugar. Okay? You never put, it's like putting the kid with honey in their bottle. You never do that. Okay, it just coats their teeth at night. Okay, you usually don't give a kid a bottle at night. If you have to, put water in it. That's the one that's not going to hurt their teeth. Because when they fall asleep sucking on a bottle, it's just going to sit there and coat their teeth. That's all it does. So do not ever put them with milk in a bottle. Lactic acid contributes that tangy flavor to yogurt and buttermilk, which you have. Okay. It also serves as food preservative to lower the pH. Okay, that retards microbial growth that causes food to spoil. So food doesn't spoil as fast if you lower the pH. You lower the pH, remember lowering the pH increases the acidity. The lower the pH, the more acidic the compound is. Okay, the more acidic it is, the less bacteria can grow on there. Because bacteria do not like an acidic environment. Lactic acid also produced in muscle cells, like we talked about. When you're exercising a lot strenuously, you do what's called anaerobic metabolism. Metabolism, the breaking down of glucose to provide energy, ATP for muscle, without the presence of oxygen, because you use it all up. Okay, once you do that, the byproduct is lactic acid, and that's what causes muscles to shut down. If the level of lactic acid in the muscle and bloodstream becomes too high enough, the muscle cannot continue to work, and that's hitting the wall. That's when you stop. Okay, oxalic acid, okay, is a dicarboxylic acid found in spinach and rhubarb. Okay, human kidney stones are often found from the calcium salt of oxalic acid. Okay, whenever the seasons change, when you go from winter to summer, and we're going to do that pretty soon here, you go from 40, 50 degree weather to 120 degree weather. And we do that in the desert overnight, as y'all know that. You know, you don't like the weather in 20 pounds, wait 15 minutes. You know how fast it can change. We can have an 80 degree change in one day. You know, you can run your air conditioning at night and your air conditioning during the day and your heater at night. The desert's famous for that. When the seasons change, the incidence in the emergency rooms of kidney stones drastically jumps because people are not used to drinking a lot of water when it's cold. And when it gets extremely hot, you dehydrate, you produce oxalic acid, you will form kidney stones. Kidney stones are extremely painful. Okay, they don't cause any pain when they sit there, but when they start to move through those tubes in the body, they hurt. They hurt extremely. Even morphine sometimes doesn't help with them. Okay, so oxalic acid is the cause of your kidney stones. It is toxic in high concentrations. Okay, foods with high level oxalic acid must be boiled before being eaten, or else you get that oxalic acid, which can be toxic in your body. Okay, and I'll give you a list of some foods that are high in it too. So oxalic acid is used in industry as a bleaching agent and spot remover. The potassium salt is used in clinical laboratories to prevent blood samples from coagulating. So when you're in the lab, you take that oxalic acid and the blood samples won't coagulate. It keeps the molecules apart. Okay. Foods high in oxalate. Okay. These are foods, if you eat a large amount, you're going to increase the amount of oxalic acid inside the body and increase your chance of kidney stones. I'm not saying don't eat these foods. What I'm saying, if you eat these foods, just drink plenty of water and realize when the weather changes, you're going to build up this oxalic acid much quicker because you're not going to dilute it. Concentrate on drinking once that weather changes because kidney stones are no fun. So here's a list of some foods that are very high in it. I know everybody loves to draft beer, right? Got to realize that's high in oxalic acid. That's not like drinking water. You can't substitute beer for water. Doesn't work that way. Okay. Eggplant, gooseberries, spinach, celery. Okay. Other foods, grits, instant coffee. Okay. Leek nuts, okra. Okay. Summer squash, tea, wheat bran, wheat germ. All those have high concentrations of oxalate in oxalic acid. Okay. 8 foods in particular have been identified as producing an increase in oxalic acid levels excreted in the urine. Now, excreting the urine is fine. As long as you drink enough water, you're going to excrete it. So I'm not saying you have to avoid these foods, but I am saying if you eat these 8 foods, make sure you drink water so that oxalic acid buildup is excreted and it's not maintained because you're retaining water. Okay, so rhubarb, spinach, strawberries, chocolate, wheat bran, nuts, beets, and tea. Okay, those are the 8 things that have been identified as producing high levels of oxalic acid in the urine. Okay, but as long as you drink plenty of water, you have no problem eating these. Okay, just be aware that's the most 8 common foods that can cause increased level of oxalic acid, which can lead to kidney stones. And kidney stones are no fun.
So if you drink the tea and then you drink water, or if you don't drink water and you're just drinking tea, the water basically cancels itself out because you're drinking tea with it?
Yeah, you're not going to have enough water to get rid of the oxalic acid that's building up.
Wow. Okay.
Yeah.
That's interesting.
You can't substitute. You can't have substitutes for water usually. I
Mhm.
mean, my wife drinks more Diet Coke and she thinks it's, oh, drinking water. It doesn't work that way.
Have you seen the water bottles that are called circles? It says circle, CIRKUL, I think it is.
Yeah.
They flavor the water in like the cap. And they're talking about like giving you more reason to drink water because it's flavored.
Okay.
But I was thinking, does that still count if it's technically flavored water?
Yes, because you're not adding extra sugars or extra, depends what you're adding to it.
Mhm.
Okay. If you got to be really careful when you do that. If they're adding sugar to it, like a lot of these power drinks add caffeine and sugar,
Mhm.
that can cause a lot of problems in the body because you're not diluting what you need to dilute.
Mhm.
Okay. Because sugar maintains water and keeps it from being excreted. You know, a lot of these sugar-free drinks that have, you know, sodium, potassium, and some of your electrolytes in it, that's fine. Okay. But a lot of times when they put sugar in it, that doesn't equal out a lot of times. And you got to be careful if you ever take these drinks and freeze them. They had a 13-year-old kid, 13-year-old, yeah, 13-year-old kid that died in New Jersey about, when was that case we went through? I think it's about 8 years ago now. He died of drinking frozen Gatorade. Okay. He was a baseball pitcher. And you know, you play baseball, you sweat a lot. Again, his mom brought him a frozen Gatorade to drink to help replace electrolytes. Now, think about this. When you take Gatorade and you freeze it, what's going to freeze? The water component. So if water component has all these electrolytes in it, okay, if you freeze the water and you start drinking some of this, you're going to get an overdose of electrolytes and threw his body into shock and he died from it. Okay. So if you like your kids, don't freeze their Gatorades. Okay. Make sure it thaws out because only the water freezes, electrolytes don't. Okay. So you got to be careful what's in your drinks. Now, a lot of the drinks like it's called ice, or I forget some of the name brands are called. They're sugar-free drinks and they have flavoring in them. Those are like drinking water. Those are fine. There's a little bit of flavor in it and your body's still getting plenty of water. But if you start adding high amounts of stuff like these energy drinks, okay, caffeine, sugars, okay, your sugar should not come from your drinks. Your sugar should come from your natural food sources. Okay, so you got to be careful what's in the drinks that you're drinking. And you can't always believe what's advertised, believe it or not. Did that help answer your question? All right, perfect. All right, tartaric acid is used in baking powder. Okay, undergo a reaction with carbonates in the dough, produces carbon dioxide. Carbon dioxide causes the bread or the cake to rise. That's where tartaric acid to your breads that you want to rise in the oven. It produces CO2. CO2 is released as a gas, it bubbles up, and your bread, your cake starts to rise with it. Okay, it's also been used as a laxative. Okay, so it's an interesting use for that. Malic acid gives you sour taste in green apples. Okay, the amount of malic acid decreases as the fruit ripens. Those the fruit becomes sweeter and less tart as it ripens. That's why you let a lot of fruit ripen before you eat it because it's very sour tasting if you eat before it's ripe, because the amount of malic acid in there. So there's a lot of malic acid before it ripens. As it ripens, you decrease that amount so the fruit tastes sweeter. Remember, low molecular weight carboxylic acids have a real nasty taste to them, real nasty smell. All right, so this is oxalic acid. This is what it looks like. Okay, it's a dicarboxylic acid. Okay, so how would you name that? Break it down as basic components. 2 carbons. 2 carbons is what?
Ethyl.
Ethyl. So ethane dicarboxylic acid. Okay. Then we can add other acids, other groups. That's tartaric acid. And you can see low molecular weight carboxylic acid. This is a dicarboxylic acid here on both ends. And then you have 2 OH groups at 2 and 3, 2 hydroxy groups. Okay, that's tartaric acid. Okay. Same thing there. That's malic acid, which you talked about. We talked about the effects of all three of these different types of acid, what they do. Okay, so one less OH group on malic acid. Okay, and again, you can tell they're just low molecular weight carboxylic acids, and they're going to have nasty taste to them. So oxalic acid, tartaric acid, and malic acid. All right. The sodium salt of benzoic acid is used as preservative in soft drinks, in pickles, jellies, and other foods, and some cosmetics it uses even. So it's the sodium salt of benzoic acid. Okay, remember, let's think about this for a second. Sodium salt means your table salt is sodium chloride. That's just your normal table salt. Remember your general chemistry, that's Na plus and Cl minus. Okay, benzoic acid is an acid. Acids means they donate hydrogens. Okay, so any acid is going to donate a hydrogen. If we have a carboxylic acid, let's put benzoic acid up here. I'll have to erase this if I have more words coming up. COOH. Okay, remember acids donate hydrogen, H plus in a solution. H plus is what we measure when we do our pH. The higher the H plus concentration, the lower the pH. So the more H plus is released from the acid, the stronger the acid. Okay, carboxylic acids are weak acids, but they still release H plus into the solution. Now, if it releases H plus, what's going to happen? You're going to have your carboxylic acid, your benzoic acid in this case, minus, and then H plus goes into solution. Okay, if you have sodium in solution, the Na plus is going to be attracted to the negative O minus. That's what we call a sodium salt. Okay, and it's strictly because the carboxylic acid has lost its hydrogen, and then H combines with HCl over here to make a balanced chemical equation. Okay, so that leaves this anion, and the anions combine with the sodium cation. So this is a sodium salt of benzoic acid. Okay, and it's called sodium benzoate, and we'll learn how to name this as well. But that's what we're talking about when we're talking about the sodium salt or potassium salts. We're talking about the carboxylic acid losing its hydrogen, which acids do, because by definition, acids donate hydrogens. They give it off and leaves behind a negative charge. And it does that because now this group here, this is what we call a resonance structure. Remember resonance structures in general chemistry? It's one that you can move the double bond around. So you can have an R group, C, double bond OO, or you can have R, C, single bond, double bond O. That was your minus sign. So the double bond can be at the top or it can be on the side. Okay, those are what's called resonance structures. They're very stable. They allow the electrons to be distributed evenly, so they're stable. So they form a negative charge and they'll get rid of that hydrogen because it's stable, it's being left behind. That's where a lot of our reactions involve the formation of water. Water is an extremely stable compound, so it pulls things around to form a stable compound. And the same with these sodium salts of benzoic acid or sodium salts of any type of carboxylic acid. So that's what we're going to be doing. And I think I got to get rid of some of the things I just drew. Okay. So that's what we mean. We talk about the sodium salt of an acid. And in this case, it's happens to be benzoic acid. But we can do this with any carboxylic acid. We can donate the hydrogen, which is a proton, leave behind a negative charge, and that's going to attract the positive charge of the salt that's in solution with it, whether it's sodium, whether it's potassium. Okay, it's going to attract the positive charge, the metal that has the positive charge on it. Okay, so if a value of preservative, okay, it is, let me get this out of the way so you can read it. All right, so it's a value as a preservative, these sodium salts, because it's colorless, odorless, and tasteless, and kills bacteria at a concentration only 0.1%. So these salts, we use nitrates, things like that, they're used in preservatives in meats and stuff. Okay, they kill bacteria. You have no color to them, so it doesn't make the food look bad. They don't smell bad because they're odorless, and they're tasteless. They don't change the taste of the food. So we can use it as a preservative. Okay, Salicylic acid is used as a disinfectant and is superior to phenol. Remember, phenol is benzene ring. That's a benzene ring with an OH group on top. Remember, that's phenol. Don't confuse it with phenol. Phenol is a benzene ring as a stitches. Phenol is a benzene ring with an OH, a hydroxyl group on top. And we use it as disinfectant, but salicylic acid is used as a disinfectant and it's better than phenols. Okay, it's also used in ointments to remove corns or warts because it causes the top layer of skin to flake off. Okay, leaves the underlying living skin undamaged. That's why we use salicylic acid. Skin cancers, when they put the acid on the face and they burn the skin, that gets through the superficial layer. Okay, and it leaves a healthy layer below it. That's salicylic acid. Acetylsalicylic acid. Okay, acetylsalicylic acid, ASA. Okay, is aspirin. Okay, you see a lot of patients writing their charts. They'll put, and when you put allergies, put ASA. That means you're allergic to aspirin. That's acetylsalicylic acid. That's the abbreviation for it. Okay. In 1897, okay, at the Bayer Company, chemically added an acetyl group to salicin that synthesized acetylsalicylic acid. Bayer was the first aspirin. It's a derivative that did not produce the severe gastrointestinal side effects caused by salicylin. Okay. It had a buffering effect. Okay. Aspirin became the first synthetic drug launching the pharmaceutical industry. So the first synthetic drug developed by Bayer Company, okay, was aspirin. They put an acetyl group on the salicylic acid and became acetylsalicylic acid. Today, aspirin is recommended in low doses by the American Heart Association, preventive measure against heart attacks and strokes caused by blood clots. Aspirin is a blood thinner. Okay? It works to thin the blood and keep blood flowing. 85 milligrams of baby aspirin prevents a lot of the blood from thickening. Okay, and works just fine. Some people need stronger doses. They'll use warfarin. Okay, warfarin is rat poison. Believe it or not, that's what warfarin is. Warfarin we give our patients as blood thinners. I've had many patients come in and say, I'm not taking this warfarin anymore because it's rat poison. It is rat poison. Okay, that's what it is. That's how it works in the body. It doesn't mean it's going to kill you. You do it in the right doses to make it work. How rat poison works, what warfarin does to a rat, is at such high doses, it thins the blood and the blood leaks out of the rat. It just leaks through all the holes in the vessels. And the rat dies because there's no more blood left inside of it. So it thins the blood to the point it completely leaks out. Okay, we're not giving that same doses that we give the rat. It's given a therapeutic dose, which makes the blood thinner. My wife's mother was on warfarin and her daughter talked her not taking it because she found it was rat poison. And she died about 3 months later from massive heart attack. You know, it's a good drug, but like any drug is poison if you're given large amounts of large enough amounts of it. I mean, it's the therapeutic dose is what you worry about. Okay, so you'll hear all kinds of things with these blood thinners, but aspirin, baby aspirin, 85 milligrams works as a great blood thinner for a lot of people. All right, so there is benzoic acid. Remember, we just talked about it a while ago. That's benzoic acid. We'll do this and finish up. Okay, that is 2-hydroxy benzoic acid. Okay, that's salicylic acid. Okay, we've gone from here. So you can see how you can add an OH group. Remember how you add with an alcohol, you add OH compound. We've done that before. We had H and OH across the double bond. Okay, with benzene rings, it's a little different because it adds just the one part and then the double bond reforms. Because this is such a stable structure, once you open up this double bond to add hydrogen again, it closes back up again. And it makes this a stable structure. Okay, giving that conjugated system, a conjugated double bonding system. So you can convert benzoic acid to salicylic acid, just for an issue. And then we convert salicylic acid into acetylsalicylic acid by adding an acetyl group to the OH group. That's 2 carbons. Acetyl group is ethanol, 2 carbons. So we add an acetyl group to salicylic acid and we get acetylsalicylic acid. And that's how aspirin is formed. Start with benzoic acid, put an OH group on it, and then substitute an acetyl group for the hydrogen. And now you have aspirin. Acetyl salicylic acid.